A loaded oil tanker has no brakes. It never did. There is no pedal, no disc, no pad, nothing on board that grabs and stops the way you imagine. And yet a vessel longer than the Empire State Building is tall, carrying 2 million barrels of crude oil, somehow comes to a complete halt in open water. The catch is the distance. From the moment the crew decides to stop, that ship will keep traveling for roughly 3 miles before it finally goes still. 3 miles. That's the length of about 44 football fields laid end to end. And the ship is moving the entire way. So how does something that heavy stop at all? What is actually slowing it down if there are no brakes? And here's the question that should genuinely bother you. If a tanker needs 3 miles to stop, what happens when there's something in the water 2 miles ahead? Stay with me, because by the end of this, you will never look at a calm, still ship the same way again. The thing keeping it in place isn't power, it's foresight. First, let's kill the idea of brakes completely, because that mental image is the whole problem. When your car stops, it's pressing rubber against road. The tire grips a hard, fixed surface, and friction does the work. The ground fights back. That's what a brake is. It's a way of borrowing resistance from something solid. A ship has nothing solid to borrow from. Water doesn't grip. Water moves out of the way. A tanker isn't rolling across a surface. It's pushing through a fluid. And a fluid will not hold still long enough to be braked against. Imagine a bowling ball rolling across a frozen lake, and your only job is to stop it by pressing your bare hand against the ice beside it. There's nothing to push on. The ball just keeps going. That is the physics problem an oil tanker faces every single time it needs to slow down. So if there are no brakes, what's left? Only 2 things. The drag of the water itself, slowly bleeding off speed through friction along the hull, and the propeller, spun in reverse, trying to claw the ship backward. Both of them are real. Both of them are working. And both of them are almost laughably weak compared to the mass they're fighting. Here's where the mass comes in, and the number is hard to hold in your head. A fully loaded supertanker can weigh over 400,000 tons. Not the steel and the cargo together. The whole moving object. That is the weight of roughly 2,000 fully loaded freight train cars. Except instead of being spread across miles of track, it's welded into one single hull, all of it moving in the same direction at once. And it's moving at around 16 miles an hour. That sounds slow. A bicycle does 16 miles an hour. But speed isn't the danger here. Mass is. Momentum is the weight multiplied by the speed. And when the weight is 400,000 tons, even a gentle 16 miles an hour becomes a wall of energy that does not want to stop and barely notices anything trying to make it. This is the trap. We judge danger by speed, because that's how cars taught us to think. But a tanker proves that weight is the real story. 16 miles an hour feels harmless until you multiply it by a mass measured in hundreds of thousands of tons. Now let's walk through what actually happens when the order is given. This is the part nobody pictures correctly. The command is called a crash stop, and on the bridge it begins with something almost anticlimactic. The engine telegraph is pulled from ahead to full astern. There's no slam, no lurch. For a long moment, nothing visible happens at all. Down in the engine room, an enormous diesel engine, an engine 3 stories tall, has to do something it hates. It has to stop turning one direction and begin turning the other. A car flips between forward and reverse in a second. This engine needs careful, deliberate sequencing, because forcing that much spinning metal to reverse too fast can wreck it. Then there's the propeller. A single bronze propeller on a large tanker can stand over 30 feet across, taller than a 3-story building, and it weighs as much as 100 cars. Picture asking a sprinter at a dead run to instantly turn around and sprint backward without slowing down first. That's what the ship is asking of that propeller. And when the propeller finally bites in reverse, it doesn't grip cleanly. It tears the water apart. The blades start churning so violently that the water around them boils into vapor bubbles, a chaotic effect called cavitation. The propeller is now half spinning in water and half spinning in froth, and that froth steals away a huge chunk of the stopping force it's supposed to deliver, so the ship begins to slow. Slowly. Reluctantly, the water drag and the screaming reverse propeller are finally winning, by inches, against 400,000 tons of momentum. The whole hull shudders with the strain, and on the bridge the only proof that anything is working is a speed reading that drops one stubborn notch at a time. But here's the part that defies common sense completely. You'd assume that as the tanker slows down, it becomes safer and easier to control. The opposite is true. As a tanker slows, it begins to go blind. A ship steers with its rudder, and a rudder only works when water is rushing past it fast. The faster the flow over that rudder, the more it can push the stern around. But during a crash stop, the ship is killing its own speed and killing its own propeller wash at the same time. The water flowing over the rudder slows to a crawl. The rudder goes soft. Then it goes nearly useless. Think of riding a bicycle. At a healthy speed, you can balance and steer with tiny effortless movements. Slow that bike down to walking pace, and it gets wobbly and twitchy. Slow it down further, and you simply fall over. A bike doesn't become safe when it slows down. It becomes uncontrollable. A stopping tanker has this same curse. In the middle of a crash stop, the captain is bringing the ship to a halt, while gradually losing the ability to point it anywhere. Which means stopping straight is not guaranteed. The ship can drift, swing, even begin to turn sideways across its own path, while it's still carrying enough energy to crush a harbor wall. This is why, with a hazard ahead, the right answer is sometimes not to stop at all. Sometimes the captain keeps power on and steers around the danger, because a moving ship can be aimed and a stopping ship cannot. Read that again. The safest choice can be to refuse to brake. Now let's put real numbers on this, because they are genuinely staggering. A fully loaded, very large crude carrier traveling at normal speed needs somewhere between 2 and 3 miles to come to a complete stop in a straight line. From the instant the crash stop begins to the instant the ship finally rests in the water, 15 minutes or more can pass. 15 minutes. That is longer than many people's entire drive to work. You could start this stop, watch a quarter of an hour go by, and the ship is still gliding forward the whole time, unable to do anything but wait for the water to win. And the math shifts constantly. An empty tanker rides high and stops differently than a loaded one riding deep. Shallow water adds drag and shortens the distance. Deep water lets the ship glide farther. Current and wind quietly push the figure around. There is no single stopping distance for a tanker, only an answer for this ship, at this weight, in this water, today. The captain doesn't memorize a number. The captain reads the situation and predicts one. None of this knowledge came cheap. It was paid for. Through the 1960s and 70s, tankers exploded in size. Shipping companies discovered that one giant vessel was far cheaper to run than several small ones, and hulls ballooned faster than anyone's instincts could keep up. Crews were suddenly handed ships that weighed 3 and 4 times what they'd trained on, and the old reflexes simply did not scale. The result was groundings, collisions. Tankers that began a stop or a turn far too late because the people aboard still had a smaller ship's timing wired into their hands. The disasters were ugly, and they were the price of a hard lesson, that a ship this size has to be stopped with planning, not reflexes. Nobody calculated the danger in advance. They discovered it, hull by ruined hull, until the new habits became law. That lesson is now built into everything you never see at a port. When a tanker approaches land, a local harbor pilot boards it, often miles offshore, climbing up the hull from a small boat. This pilot knows that exact stretch of water and starts slowing and positioning the ship long before any dock is in sight. It's a little like a valet who has to begin the parking maneuver while the car is still several streets away. Tugboats escort the giant in, ready to pull and brace, Because the tanker cannot trust its own rudder at low speed. Shipping lanes are split into carefully separated one-way corridors, so two of these unstoppable masses are never aimed at each other. Speed limits inside harbors exist for one blunt reason. A slower ship needs less room to stop. Every drop of fuel that reached your car, every product that arrived in a plastic bottle, crossed an ocean inside a hull that could only be brought to rest by someone thinking 15 minutes and 3 miles ahead. So go back to that image. A tanker sitting perfectly still on calm water, looking parked, looking effortless. It was never parked. What you're looking at is the final frozen result of a decision that was made miles back. A slow and deliberate negotiation between a wall of momentum and the patient drag of the sea. The stillness isn't the absence of motion. It's motion that was defeated, gradually, by foresight instead of force. A tanker doesn't stop because it's powerful. It stops because someone saw the future early enough. But stopping is only half of the puzzle. Because once you understand that a rudder goes useless at low speed, a stranger question opens up underneath it. How does a ship, this enormous steer at all, with no road, no wheels, and nothing under it but water, that refuses to hold still? The answer is far weirder than a steering wheel, and it depends on a trick most people would never guess. That's the